Let's solve first missing positive. So in this question, you're given an unsorted integer array nums, and you just want to return the smallest positive integer that's not present in that array. And a follow-up is that you want to do it in linear time and ov1 auxiliary space. So in this case, if you look at this example, well, a 1's there, a 2's there. Well, the first positive integer that's not there is going to be a 3, so you just return a 3. In this case, well, 1's there, well, 2's not there, so you return a 2. And in this case, well, these are all really big positive integers, and it's missing, well, 1. So you return 1. So quite an easy question to understand, but maybe a bit more difficult of an algorithm. So I guess one thing to note first is that when you're looking at these numbers, you kind of want to have you're never going to check, well, for this one of size 4, you're never going to check, well, is a 6 in there, is a 7 in there? No, you want the smallest positive integer. And in this case, you would ideally just check, well, is there a 1 in there, a 2, 3, 4, and the only case you have to check if there's a 5 is that if the array itself is perfectly it perfectly has every element, and in this case, well, you don't want to return 4, you actually have to return 5. So the key idea is you just want to basically loop up until the length of the array, and sometimes I guess the length of the array plus 1 if it's perfect. But yeah, you really don't have to look at any other numbers. Another idea is that you don't care about any of these negative numbers, right? Because a negative number will never contribute towards one of the actual answers because you want positive integers. Another thing to note is anything greater than the length, like maybe 5, also doesn't matter. So yeah, let's try to think of how we can solve this problem. So the brute force methods are, why don't we loop through the entire array nums and check, well, is a 1 in there, is a 2 in there, until we reach one number that's not in there, it's missing, and we can simply return that. So in that case, the time complexity would be actually quadratic because you were doing the lookup, which takes O of n time, which then might allow you to think, well, why don't we just put nums into a set? And then now if we do constant lookup times, yeah, you'll have O of 1 time. So basically you can reduce it down to linear time. And I think Leetcode actually, I think the solution actually passes. But in this case, because you're using a set, this has O of n space. So now let's look on to the intuition of how we can achieve a solution in linear time and constant auxiliary space. And what auxiliary means is that technically it's linear space right now because we've been provided an array of n elements. But auxiliary just means we can't introduce any new space data structures, but rather we can only work with manipulating the current space that we have. Okay, so how can we do this? Well, we learned earlier that we only have to really look at numbers from 1 all the way to the length of nums, right? We're never going to check, well, is 9 in here? Well, the length is only 4, so there's no point in us checking the answer 9 because an answer would most likely fall within this range. And also, quite frankly, the indices also kind of go from this range, right? It goes from 0 to 3. It's just off by 1, right? So let's kind of use that to our advantage. We see that ideally, what if we got a new array where all these elements were in the correct positions, right? So in this case, what if the 3 was here, the 4 was at the very end, the 1 was in the first position, and then of course we have -1. Well, in that case, we don't know where to put it. There's one spot left, so we'll just put it here. If we can get it to sort of look like this array right here, then it's very easy to tell which number is missing, right? Just do a linear scan upwards. Well, we see a 1's in the correct position, so that's fine. Well, there's supposed to be a 2 here, but there's not. Therefore, we can just return 2, and that is indeed the smallest integer missing. So yeah, let's try to do that approach. How do we get from this array to that array? Well, like we just did, it's a bunch of swapping. So this is how the algorithm works. You look at the first number 3. You want it to be at the third index, or the third position rather. So we just swap it so it becomes this. And then you see that now you have -1 here. Well, is it in the correct position? Well, because it's negative, we don't really care about it, so we'll assume it is in the correct position. Then you look at the next number, 4. you want to swap that to the right place. So we're going to do the swap again. So now 4 is in the right place. And now you're looking at this 1, right? Now a 1 is here. Well, we know that it's not in the first position, so we actually have to swap it again. So in this case, we're going to swap this one down here. And now the 1 and the 4 are in the right position. And also, quite frankly, when we go here, right, now the green arrow is going to look at this 3. It's in the right position, so you don't have to do any swaps. Then I'll look at 4. It's in the right position, so you don't have to do any swaps. And just like that, you've constructed the array. And by doing this, you'll always end up with the correct order. So like every number that's present is going to be in the correct position. So now that we have this array, just do the linear scan again, and then return the result, and that's it. So in this question, what is the time complexity of sort of transforming it to this? Well, it's actually going to be O of n time. And the reason why is that you're going to have at most n swaps because each swap puts a number in the right position. So in total, if you're putting every number in the right position, that means you're going to do at most n swaps, which is why it's O of n in time. And then at the end, when you do the linear scan from 1 to length of nums to check if the number is in there, that's also just a linear scan. So in total, the time complexity of this algorithm is O of 2n, but this is equivalent to O of n in big O. And in terms of space, well, we haven't introduced new data structures. We just sort of took advantage of the indices and positions. So this is O of 1 space, and that is the entire algorithm. All right, so now let's write the code. So we want to loop through all the elements and kind of decide whether we want to swap. Well, we first have to make sure that it's valid, right? And how it's valid is if it's between 1 and the length of nums, right? These are all the valid positions. If you gave me something like -3, then there's no point in swapping it because there's no position -3 to swap it into. And also, it's possible to do many swaps, which is why we're going to do a while loop. If we had something like this, well, the other condition is that, yes, 2 is between the range, but also, what if it was like this? There's no point in doing a swap, right? Because 1 is already in the correct position. So we only want to do a swap when it's not in the correct position, like this. And how do we check that it's not in the correct position? Well, it's when nums at I, which is, in this case, the first iteration is going to look at the 2. When it does not equal the element at position 2. And how do we get the element at position 2? Well, it's nums at I minus 1. So this gives us this 1 right here. And you can see that the 2 does not equal the 1, so therefore the 2 is in the wrong position. So we should perform a swap. In Python, swapping is quite easy. And we have to do it in this order. So nums at I and nums at I minus 1. So we did the swapping. Now that basically is the entire algorithm. Now we can just simply loop through it and check, well, which numbers are we missing? And how we check that is if nums at I does not equal I plus 1, right? This is the position, which is why we're adding 1. So if this doesn't happen, well, we found one that's missing. And because we're going in increasing order, this will be the smallest possible answer. So we return I plus 1. And in the case that we have like a perfect array, like 1, 2, 3, 4, like all numbers are included, then we won't hit this actually. So what we have to do is just return length of nums plus 1. And we can run this code and hopefully it'll work. Yeah, it seems like it passes.